Can I listen their voice?
Yes, sir.
Or it is muted? I can't see them. Good afternoon, my dear students.
Good afternoon, sir.
Good afternoon, sir.
All of
Good
you.
Good
afternoon.
afternoon, sir.
I think it is sleeping time for you, isn't it? You had lunch? Yeah. So today I'm here to discuss about colorimetry. Okay. So all of you are safe, I hope, right? I can't listen any response. Okay. Anyway, I'm going to start about the colorimetry today. So colorimetry is a measurement of color. So this is COLOR and metry means measurements. So measurement of color, it's called as colorimetry. Is it audible, guys?
Yes,
Am
sir.
I audible?
Yes, sir.
Yes.
Yes, sir.
Okay. So measurement of color is called colorimetry. Okay. There is one more calorimetry, that is CALOR. So that is about measurement of calories. You all know like calories, right? So usually for the nutrients we used to measure with calorimetry. But this is the different one. It is the colorimetry where we measure the color of the solution. Okay. Why we need to study about the colorimetry? I'm going to discuss today. So what is the importance of colorimetry? Okay. Colorimetry is measurement of colors. So to measure the colors, this is the instrument called colorimeter. Okay. So this colorimeter can measure the colors which are in the range of visible range. Okay, that is 400 to 700 nanometers. So this is an instrument which is used to measure the colors of the solutions. This particular instrument is operative only visible range, that is from 400 nanometers to 700 nanometers. Okay. So what is wavelength? So if you see these waves, okay, between two waves, the distance between two waves is called the wavelength. So here there are gamma rays, X-rays, ultraviolet rays, and this is the visible range, that is 400 nanometers to 700 nanometers. So calorimeters only can deal between these nanometers. This is the visible range light. Okay. So above 700 infrared radio waves are there. Okay. So below 400, these are gamma rays, X-rays, ultraviolet rays. These are all below the 400 nanometers. So this is the wavelength between the two waves. The distance between two waves is called the wavelength. So when wavelength is increasing, energy will decrease. So when wavelength is decreasing, energy is increasing. These are indirectly proportional to each other. So what is the principle on which this calorimeter works? Okay. So when a white light, okay, that is from the tungsten bulb, when white light pass through a solution, that is a colored solution, some of the light gets absorbed in the solution. Okay. Then some amount of light will be coming out of this solution. Okay. This is I0, this is I. So when white light passes through a color solution, it is going to absorb some of the color and emit the lesser range of the disturbance. the principle on which this calorimeter works.
Hello.
Chandra, ನೀನು ಹೋಗ.
Hello.
Wait guys, they have muted all.
ಎಲ್ಲ ಮ್ಯೂಟ್ ಆಗ್ಯಾವ ಸ್ಟೂಡೆಂಟ್ಸ್.
ನಾನು ಇಲ್ಲಿ ಕ್ಲಿಕ್ ಮಾಡೀನಿ, ಈಗ ಅನ್ಮ್ಯೂಟ್ ಮಾಡಬೇಕು. ಅದು ಡಿಸ್ಟರ್ಬೆನ್ಸ್ ಬರ್ತಿದ್ದ.
ಹಾಡಿದ್ದು ಅವ್ರು ಮಾಡ್ಕೋಬೇಕು ಸರ್, ಅವ್ರು ಮಾಡ್ಕೋಬೇಕು ಸರ್ ಇಂಡಿವಿಜುವಲ್.
ಅನ್ಮ್ಯೂಟ
ನಿಮ್ಗೆ ಏನು ಡಿಸ್ಟರ್ಬೆನ್ಸ್ ಬರೋದು ಸರ್? ಈಗ
ಮ್ಯೂಟ್ ಮಾಡೀನಿ.
ಮ್ಯೂಟ್ ಮಾಡ್ರೆ ಸರ್.
ಎಲ್ಲರಿಗೂ ಅನ್ಮ್ಯೂಟ್ ಮಾಡ್ಬೇಕಂದ್ರೆ
ಈಗ ಸರ್ ಯಾರು ಕ್ಲಿಕ್ ಮಾಡಿ.
Guys, whoever wants mic, you can turn on the mic and you can ask me questions in between. Okay. So when white light pass through a colored solution, it is some of the light is going to absorb in the sample and some of the light will be coming out of this tube. Okay. It all depends on the concentration of the solute and the path length of the tube. So this is the schematic representation of calorimeter. So in the calorimeter, we'll be using the tungsten lamp, which will emit the white light, and we'll be having slit, which will allow only portion of light. And we will be using the condensing lens inside the calorimeter. So this condensing lens will filter some of the colors of the light, and it will only transmit required wavelength of light. And this is the cuvette which will be containing the solution in color. And from this cuvette, light will pass through this cuvette and it will hit the photocell. Whatever light is falling on this cuvette and coming out of this cuvette, so this light energy we cannot directly measure. So whatever the light is going to hit this photocell is converted into the electrical energy. This electrical energy will be measured by the galvanometer. So this is the main principle of the calorimeter on which it works. So tungsten lamp, this slit, condensing lens, and there will be specific filters for the specific range. Suppose 400 nanometer filter, 700 nanometer filter, 450, 500. So there will be different filters which we will use to selectively transmit particular wavelength of the light. Then this cuvette will be containing our solution, that will be in a colored form. So whatever the light is falling on this is going to pass through this cuvette and some of the light gets absorbed in the solution, then it will be hitting this photocell. So this light energy will be converting into the electrical energy, and that electrical energy is going to be measured by the galvanometer. So color, what is color? So color results when radiation is absorbed by an element or by a compound formed through a reaction. So to develop particular color, we are going to make specific reaction that will only react with the specific solute and it makes the color. So this is the tube and which is having the solution. So this is the white light and it will be passing the red, yellow, blue color lights through the filter, and this red color is going to be absorbed in the solution and only yellow and blue color lights are going to be emitted. So this is, there are some terminologies which you have to know. That is the most important thing is the transmittance. What is transmittance? Transmittance is the ratio of the intensity of light leaving the solution to the intensity of the light entering the solution. When there is a test tube, when light is passing from this side, so the intensity of this light will be more than the light coming out of the test tube. That means some of the light is going to be absorbed in the solution. So this is, transmittance is the ratio of the intensity of light leaving the solution to the intensity of the light entering the solution. So it will be indicated by I and I naught. So transmittance, I am going to show the same thing in the schematic. So this is the light which is passing through this solution, and some of the light get absorbed in the solution and this much light will be transmitted. So T, transmittance, is the ratio between the transmitted light between the initial light. Percentage of transmission, it is the formula T into 100. T is the ratio between the I and I0 and percentage transmission is T into 100. So here there are, calorimeter mainly works based on the two principles, that is Beer's law and the Lambert's law. So based on these two laws, this calorimeter works, and we are going to measure the concentration of any solute by using the biochemical reaction, and these two laws are behind this calorimeter principle. So first we are going to discuss the Beer's law. Beer's law says like concentration of the substance is directly proportional to the amount of light absorbed or inversely proportional to the logarithm of transmitted light. Which means like suppose your light source is here and you are passing the light through this cuvette which is having the solution which is in color. So the absorption of this color is mainly depending on the concentration of the solutes which are there in the solution. Suppose if you are estimating the glucose, if glucose concentration is more in that particular reaction, so there is a method called glucose oxidase peroxidase method. Okay, so if there is 100 mg of glucose there in the solution, that gives little intense color. If it is 200, color intensity will be almost double. So the absorbance of the light depends on the concentration of the solutes or substances which are present in the solution, and it is inversely proportional to the transmittance. That means little light will be transmitted through this solution. So A, absorbance is directly proportional to the concentration of the substance or solute. This is the Beer's law. Transmittance, transmittance is the light which is coming out of the test tube which is having the colored solution. So transmittance is going to decrease with increase in the concentration of the substances. So initial transmittance, if you pass the light through empty test tube, the entire light will pass through that, almost 99.9% of the light will pass through that test tube. Okay, that is I0. If there is light color, so transmittance will decrease this much. So if 1 unit substance is there, so transmittance is going to decrease, so it will going to decrease further if you increase the substance concentration. So this is the transmittance. Mainly Beer's law says transmittance of light is inversely proportional to the concentration of the solute. Absorbance is directly proportional to the concentration of substance. So this is the Beer's law. Suppose 100 mg per dl of glucose is there. This absorbance will be here. It is 0.1. So for absorbance there are no units. Only concentration we will be mentioning the units. So concentration goes on increasing 100, 200, 300, 400, 500 and 600. So this absorbance is also increasing according to the concentration of the substance in the solution. So transmittance is going to decrease, absorbance going to increase according to the Beer's law. There is one more law based on which our calorimeter works. So our calorimeter works mainly based on this Beer's law and the Lambert's law. So Beer's law says the absorbance of light is directly proportional to the concentration of the substance. Lambert's law says when a ray of monochromatic light passes through absorbing medium, its intensity is going to decrease. If you see the intensity of this color, it is reduced after passing through the solution because this absorbing medium is absorbing some amount of the light. So when a ray of monochromatic light passes through an absorbing medium, here absorbing medium is the solution, its intensity decreases exponentially as the length of the light path through light absorbing material increases. Suppose this light path, this width of the cuvette is this much. If light path if you still increase this much, double, so absorption of light also increases more. So that is the Lambert's law. So Beer's law says absorption of light is directly proportional to the concentration of the substance. Lambert's law says absorption of light is directly proportional to the width of the medium. That is the path length. We call it as a path length. So if you put bigger one, so absorption of light is going to increase. This is the Lambert's law. Absorption of sample of concentration. The path length is the B. So this is the transmittance. So the absorption of light is going to increase when you increase the path length. So this is the graphical representation of the transmittance. So when the optical path increases, transmittance gets decreases. So this is the graphical presentation I am showing. Here 1 unit of path length, transmittance is this much. If it is doubled, transmittance got decreased, it got further decreased if you increase the path length. So this is the Lambert's law. So Lambert's law says about the path length. Beer's law says about the concentration of the substance in the solution. So these two laws are more important, and examiner going to ask you in your practicals as a viva question, or you may get as a short answer. We don't know, but you have to write. If they ask you about the Beer's law, or if they ask you about the Beer-Lambert's law, you should be in a position to explain what is Beer's law. If they ask, you should say like absorbance of light is directly proportional to the concentration of the substance in the solution. And Lambert's law says absorbance of the light depends on the path length. If path length increases, absorbance also increases and transmittance decreases. So how do we use this principle? Colorimetry principle, why we are learning it? So why it is important in the biochemistry laboratory? So to perform chemical reaction with element to be analyzed that results in a compound of that element that absorbs light. Suppose if you want to estimate the concentration of glucose in a solution, so how you are going to do that? So there will be a chemical reaction which specifically reacts with glucose and forms some final color substance. That color substance, that color intensity will be directly proportional to the concentration of the glucose. Here I am giving you glucose as an example. Okay, so there are so many other diagnostically important biochemical parameters: glucose, urea, creatinine. Okay, so these are all uric acid, calcium, so many biochemical parameters we are going to measure, okay, in the biochemistry laboratory. So these are all measurements depends on the colorimetry principles. So nowadays there are fully automated instruments, still those will follow these principles. So this indirect measurement is based on the amount of light absorbed. So if the intensity of color is more, absorption of light will also increase, and it is going to give indirect measurement of that particular substance. So the amount of light is absorbed to the chemistry involved, and it depends on particular factors: the chemistry behind that reaction and length of the light travel, the amount of absorbing material, how much absorbing material, that means like if you take glucose as example, so it depends on the glucose concentration. So finally, these Beer's law and Lambert's law combined together. So one law is saying like absorbance of light or the transmittance of light is depends on the concentration or the path length of the tube. So they finally combined these two laws. Okay. So they says like absorption of light depends on the concentration of the substance and the path length of the solution, or the path length of the cuvette or tube which you are using for that experiment. Calorimetry, measurement of the light, so we discussed, and by the color developed in a sample. Sample may be like our serum sample. If you think about the human sample, most of the time serum or synovial fluid or cerebrospinal fluids, so many other kind of samples we will use in the clinical biochemistry laboratory to measure particular substances in the sample. So concentration can be calorimetrically determined if, suppose if you want to estimate glucose, okay, so what kind of chemical reaction we should choose? So glucose, whatever the chemical reaction which is going to happen, that should be with only glucose. So whatever the color is going to develop, that should be because of the glucose only. So then we can estimate the concentration of glucose in that particular sample. And the second point is the developed color obeys Beer's law over a reasonable range of concentrations. And the developed color must be stable for reasonable length of time, reproducible and sensitive to small changes in concentration. So whatever the color is produced by this chemical reaction, if it is not stable, suppose if that color is disappearing within seconds, before you measure that color using the calorimeter, it may change, color intensity may change. So then you may not get the proper values. So the color must be stable and for reasonable length of time, and it should be reproducible. So at any circumstances, so that should be reproducible, and it should be sensitive enough with that particular substance or to small changes in concentration. Suppose if particular substance concentration is very high or very low in the sample, this reaction should be in a position to give the color. And the fourth point is all loss of transmitted light must be from absorbance by substance measured. Suppose if you are using serum sample, so if you are measuring glucose, you cannot use directly blood. Okay, you should you can use directly blood, but some of the factors may influence the values of the glucose in that particular condition. If you want to measure the total proteins if you want to measure, you have to separate RBCs and other things from the blood sample. So for that we use the centrifugation technique. So by using centrifugation, we are going to centrifuge all the red blood cells, and we will be separating the serum from the sample, and in that particular serum we are going to measure the proteins. Okay, if you want to measure some lipids, that time we are going to centrifuge and we are going to use the serum sample. So, and there are some methods where we are going to take out all RBCs or all proteins from the sample, then we are going to measure those particular substances. For example, nitric oxide or malondialdehyde. So nitric oxide is the vascular relaxing factor. So these things should be removed to avoid the interference in the reaction. So all substances present in sample must be available for reaction with color developing agent, and we should be able to measure amount of light absorbed. So then only we can determine the concentration of the substance. So to measure the concentration of any substance, we need to prepare sample. So sample dilution may be required, and we should remove some solids from the sample. As I told, like RBCs will be removed, and we are going to take serum or plasma to measure particular substances. Okay. So sample preparation is more important. So some of the substances which are there are going to interfere with your actual readings. So you cannot be able to measure the concentration of that particular substance. And also pH is one of the important factor. So pH we should always keep constant in all the reactions, in all the samples or the standards, so that we will get the standard readings. So we should digest some of the organic compounds if you are measuring something from plants or something. So we should take out these organics. And calorimetry, we are measuring the colors obviously, and the color must be stable, and this reaction should be reproducible whatever the reading we are taking. So if you are measuring a particular color, for suppose for example 100 mg per dl of glucose is giving this much intensity of color, if you do next time, so same amount of absorbance it should show. So that is the reproducibility. And sensitivity. So if concentration of glucose is very low, maybe 10, 20, that time also that particular chemical reaction should be able to produce particular color. So color development we must control the pH, and we must control the time. Suppose like if you are starting the reaction and you are making that to allow to get reacted for 5 minutes, so everything should be maintained at that particular condition. So temperature also we should maintain, and ionic strength also we should maintain. So measurement of the amount of light absorbed by the color developed in a sample. So that is the colorimeter. So the same thing. Actually, how you are going to measure the concentration of any substance in a sample? So always we will be using the standards. Standards contain the known amount of the same substance. So suppose if you are estimating glucose, standard will be pure glucose molecule. So which is going to react with the different reagents, and it will produce some color. Suppose 100 mg per dl of glucose is going to give 0.2 absorbance. So unknown sample, you don't know how much concentration is there. In that condition, you are going to get the absorbance value. So there are some mathematics behind this. By using those formulas, we can calculate the concentration of that particular glucose in the unknown samples. So these are the color comparators. Like, it has been evolved so much. Earlier they used to compare the colors with neck dyes. Later on they started using some instruments. Now we are using colorimeters. So some compare sample color to known standards. So advanced thing is the spectrophotometer. See here. So if you see the intensity of the color, so this is the blank. Blank is a solution which is not having any reaction or any substance in that which is going to produce any color. So this is called blank, and this is the concentration 0.2 ppm, 0.4 ppm, okay, 0.6 ppm, 0.8 ppm. If you see the color intensity, as the concentration increasing, color intensity of these solutions are also increasing. Okay, so that's what Beer-Lambert's law says. So we are going to use calibration curve to for the graphical presentation. By using that calibration curve, we can calculate the concentration of the substance in unknown solution. So I'm just showing you the instrument. This is the calorimeter. So this is very old instrument photograph. So some of the other, so there are so many manufacturers who makes these calorimeters. So this looks like this, but principle behind these things will be same. There will not be much difference. So how we should operate this instrument? So unfortunately you are not here, otherwise I might have shown the calorimeter with the particular examples and all, and also you can be in a position to handle that instrument. So instrument, initially we should warm up and we should set monochromator, and we have to set absorbance at what absorbance we want to take the reading, and also we should set it to 0 to avoid any interference of the external things. So we have to use this blank for that, because some reagents will be having their own color. So that color we should avoid. That absorbance of light by the reagent color we should avoid. So we call that as a reagent blank. Some people will use plain distilled water, that is the just blank. If you are using reagent, that is reagent blank. So this is the instrument operation. So this is the absorbance between 0.1 to 0.7. Some analysis more restrictive. So best readings between lowest and highest standards. Suppose if you are running two standards, one will be suppose 0.2 ppm and another one will be 0.8 ppm. So if unknown sample also contains the particular substance in in between these two high and low range, so only you will be able to measure that particular concentrations. So if it is going below the lowest, if it is going beyond the highest, then we should not consider those concentration. That time we have to dilute our sample and we have to redo the test. So calorimeter calibration. So calibration is like checking the instrument's functionality. So calibration are standardized by measuring absorbance readings of a series of known standards, as I shown in the previous slide. So we know the concentration of that particular substance and we will measure the absorbance. So 0.2 ppm concentration, how much absorbance it is showing, 0.4 how much absorbance it is showing. So that we are going to tabulate, and we will also make calibration curve as well. Then we are going to measure the absorbance of the unknown solution where we don't know the concentration. Our aim is to know the concentration of that particular substance in that sample. So comparison of these readings to the reading for a sample. So we can use computer spreadsheet, or some instruments will be having internal microprocessors. They will calculate all these things in the background, and those will give you the results. Or you can plot a graph and then you can measure the actual concentrations. So we should verify this more frequently. At least one standard we should check, and it should be in acceptable range, and each time samples are, whenever you analyze the samples, you should also analyze some standards as well to know the instrument functionality. So we have to repeat the calibration, significant change in procedure, equipment or reagents. So every time you will be changing your reagents, or your equipment might have changed. Okay, that time you have to calibrate your instruments. And also we have to determine the length of time. So how much time you have stored your reagents. So the reaction will also depend on the uh, reagent stability. And verification standard not in acceptable range. If standards are not coming in the acceptable range, then you have to prepare your fresh reagents and you have to redo the tests. So calibration steps: prepare stock solution, prepare series of dilution. So these are all I'm explaining you why these are all factors important to use the calorimeter. Even though if your calorimeter is working fine, if you are not able to calibrate it properly, then you may not get the reproducible results. So, and that whatever the chemical reaction is happening, it should be able to develop a kind of color, and we have to measure that absorbance, and we have to prepare the calibration curve. So here I am going to explain how we usually measure any kind of substance in the biochemistry laboratory. So here I am going to take certain example like glucose estimation. Okay. So for that we usually take blank, some series of standards, and the test. So blank, either reagent blank we will be taking, or the pure distilled water we will be taking as a blank, and standards of known concentration of glucose will be there. Some range of standards we will be taking, and the test will be the sample from which you are estimating the concentration of that particular substance. So these three are the important things. So what is blank? To eliminate, why we use blank in any of the this calorimetry related procedures? So to eliminate the effect of light absorption by the reagent used. Okay, if you take solution, if your cuvette is fine, that cuvette and that particular water also absorbs some amount of light. Okay, to eliminate those interferences, you have to use the water blank. Some of the reactions require reagent blank. Suppose if your reagent itself, the reagent which you are using to make chemical reaction and produce final color, so that reagent blank also should be used to avoid the interference of the any absorbance of light. So that is kind of correction we are going to do by using the blank. So what is standard? So standard is a solution of known concentration of the substance. So standards, series of standards we will be taking. We know the concentration of that particular substance in those solutions, and we can clearly see the color intensity differences. So low concentration, color intensity will be very less, and high concentration, color intensity will be very high. So these known concentration of solutions we will be using as the standards. So both OD and concentrations are known. OD is optical density or absorbance we call it as. So concentration of unknown can be calculated. So standards are used to calculate the unknown samples concentration. So test solution is made by treating a specific volume of the test sample with reagents. So suppose you may take 100 microliter of serum to estimate the glucose, or you may be using only 10 microliter. So that is the test we call it as. And we will be doing that reactions as per the protocol. Suppose if you are estimating urea, protocol will be different and reagents will be different. If you are estimating glucose, protocol and all these reagents will be different, and the particular wavelengths are also different based on the color which that particular chemical reaction is going to produce. So this is the formula. By using this formula we can calculate the concentration of test solution. So Ct is the concentration of the test solution, At is the absorbance of test, As is the absorbance of the standard, and Cs is the concentration of the standard. So this is the formula if you are calculating for per 100 ml. So absorbance of test divided by absorbance of standard into concentration of standard into xml into 100. So xml means how much amount of sample you are taking to do that particular reaction. So usually if you see any of the reports, glucose values will be mentioned most of the time per dl. Per dl deciliter means 100 ml. So concentration of test. So this is the formula, and see OD of test minus OD of blank. I told you to avoid any interference of light absorbance by the cuvette or the solution or the reagent which we are using for that reaction. We have to subtract that value because the absorbance of light is because of this thing. So this is the correction we are going to do. OD of test minus OD of blank divided by OD of standard minus OD of blank, and amount of standard divided by volume of standard into 100. So this is the formula which we can use to calculate the concentration of the test. So I'm just showing you the calibration curve. So if you see this graph, this is x-axis and this is y-axis. So on the x-axis we have mentioned about the concentration. So this particular thing is for the total phosphorus. Okay, this is the phosphorus concentration: 0.1, 0.2, 3, 4, 5, 6, 7. Okay, this is the absorbance value. Absorbance is the light absorbance, how much amount of light is getting absorbed by this solution. So 0.2 concentration absorbance is 0.104. So this is 153, 210, 258. So as the concentration is increasing, the absorbance is also increasing. So 0.2, 0.3, 4, 5 and 6. So these two are increasing based on the concentration. So I can tell you, like, so this is about the standards. So once you get this calibration curve, now if you have analyzed suppose your test concentration is somewhere here, so you have to draw the line something like this. Okay, this is the test absorbance. So you will be knowing only absorbance of the test. So you are going to plot that line and it is going to give you the concentration of that particular test. So this is the use of the calibration curve. So we are going to calculate concentration of the substance in unknown solution by using the calibration curve, so that it should not go below this, whatever the substance you are analyzing, it should not be less than the lower concentration of the standard, it should not be beyond this standard. So if it goes beyond this or below this, we're not sure about that particular reaction or the value whatever we are getting, we cannot believe on that. So we should always take the absorbance value which is in between these two ranges. If it is going beyond this, that time you need to dilute it so that it should come somewhere below this ranges. So thank you. If you have any doubts, I will be happy to answer. You can unmute yourself and you can ask me any questions, or you can type in chat box as well. Any questions? Any questions, guys? Please unmute yourself and ask me questions. Please unmute yourself and ask me any questions if you have. कुछ क्वेश्चन है तो पूछो करके. Students, if you have any questions, please ask me. Otherwise, I am going to end this session. Please unmute yourself and ask me any questions if, or you can type in the chat box.